Hi, everyone, and welcome to this webinar. Today, we're really happy to be introducing Dr. Hergen Schultze from the head of data analytics at BASF Research on his webinar entitled Big Decisions with Small Data, How to Navigate Trade-offs in Data-Driven Optimization of Complex Businesses. On my own, my name is Theo. I work as the head of Data Scientist Germany, handling our activities in the DACH region. And Data Scientist, in just a couple words, we are a training institute specializing in, you guessed it, analytics and data science. Now, before we start off things, just a quick reminder that you can always ask your questions, whatever the platform you're on, whether it be YouTube or LinkedIn. So don't hesitate to challenge us and ask plenty of questions that we'll be able to showcase throughout the journey. I will be the presenter here, but without any further ado, let me introduce Hergen Schultze to the scene and hand the floor over to him for the introduction.
Yeah, thank you very much. First of all, thank you to the organizers. Thank you for the invitation. Thanks for the opportunity to speak about one of my favorite topics here. So today it's all about big decisions with small data. And you can guess from the picture, the data we are talking about is experimental data coming from labs, data that is measured. And I will talk about that a little bit more in the minutes to come, but that's the reason why the data is small. Big decisions because we as scientists, we decide whether a product is developed or not, how a product is developed, how a process is designed. And so we decide very early on about the properties of the products we buy. So we as data scientists, we always have to think about, okay, what is our value proposition? What do we really want to achieve? Here in this talk, it's all about optimization. You will hear a little bit more details, and you will see why optimization is such a key here in this problem. Our proposition is that we speed up data-driven decisions that are based on such small data sets. Moreover, we promise that the discussion between customers and suppliers, so typical B2B relationship, gets much more transparent with help of the models we create. And third, we make everyone, the customer as well as the supplier, an expert on the products with the help of the machine learning models, and we help to navigate all the optimal decisions that could be made. All right. So the rest of my talk is separated into 3 sections. In the first section, I'm gonna dive deeper into the problem, talk to you about why the data is small and why the problems are of that kind. In the second section, I will describe the methods that we use to actually solve the problem and the digital product that we created. And in the last section, I will give you an example. I will talk to you about or talk you through a success story that we have achieved together with the customer. All right. Small data. Why is the data small? So, in an experiment in the real world typically costs you between 100 and 10,000 euros. 100 euros is really a small, inexpensive experiment. And if tests get really complicated or long term, it can easily cost 10,000 euros. And the result is one line in your table. Okay? Each line in your table costs 100 to 10,000 euros. So that means if you have for a specific problem a data set of 100 lines, 100 points, you're very, very lucky. Typically, you have less than 100. All right, that wouldn't be a problem if we just need to fit a straight line. But we have many variables. An experiment is controlled by typically tens of variables. There are the recipes, the different ingredients that go into a product. There are the process conditions. How is the product produced? So they easily sum up to 10, 20 different conditions that you want to model. And it's not just one thing that you measure. You're interested in multiple things. You're interested in multiple product properties. So you want to create multiple models. And all that with the small data set. So that describes the problem, and that's why AutoML doesn't work. Now, I already said we are looking at multiple objectives, multiple things we measure and we want to optimize for. Why is it so? So I give you two examples from BASF. So these are two examples out of thousands, obviously. So BASF is producing thousands of different products. And one example are cathode materials. And cathode materials for batteries. Yeah, so in a typical car battery, you might find BASF materials. And these materials are complex. They consist of multiple components, and we want to optimize the performance of the material and at the same time reduce the carbon footprint. These are two objectives that hopefully go well with each other, but physics is hard, so they often do not go hand in hand. Completely different example. We produce binders for paints. The success story I'm talking about at the end will be from that industry. Again, we want to reduce the emissions of our products, but at the same time, we want to improve the properties. And here we see an example of multiple properties. So we want to increase the opacity of the material and the scrub resistance. Again, if you are lucky, the opacity and the scrub resistance go hand in hand. But again, physics is difficult. And the most opaque material might not be the highest resistant material. And typically these properties do not go hand in hand. So they are in conflict with each other. As a result, your problem becomes what mathematicians and economists call a Pareto optimum, a Pareto problem. So there is not one solution. There is an infinite set of compromises, an infinite set of Pareto optimal solutions. So a little bit more structured now, and to be clear what we are talking about and to introduce the terms correctly. The 10, 20 variables that you can control, the recipe, the process conditions, that's called the decision space. You can also call it the input space. To learn, or to I already said learn, to construct the model that takes you from the inputs to the outputs to the objective space, this process is called learning. This is machine learning, building the model that links all the inputs to all the outputs. And I already said outputs are also many: quality, price, and all the different material properties. But what we actually want is a special point, or as I said, the Pareto front in that objective space. So we have the inverse problem. We want to build a connection between the objective space and back to the decision space. And that's called mathematical optimization. All right. Now we set the scene. We know the data. We know the problem. So what do we do? First, when you want to build a solution, have the user in the center. Think about the user. And the user is a lab scientist that is conducting experiments. Okay, so what does the lab scientist do? How does the workflow look like? It always begins with stating the problem and defining the variable. So selecting the ingredients, selecting the processes, defining the decision space, and defining what to measure and what to optimize for. So the objectives and the factors. All right. But before we do experiments, it's actually very important to design the experiments and hopefully even take into account previous experiments and do this design in an iterative fashion. I will come to that in the next slide, because this is a numerical step before we actually gather the data that we can learn from and optimize with. So, yeah, looking at the workflow of the users, we have actually identified another problem that the user has before we can actually solve the Pareto optimization problem. This is an old problem, and the solutions are very old. Nevertheless, most people don't apply them. So I reference a book from Fisher from 1935, where he laid out all the essential mathematics. So this is kind of solved. What is design of experiments about? If you think about the picture in the middle, that's the simplest case. Yeah. So we have data, and we have one variable and an observable. So we want to learn y as a function of x, and we assume it's a straight line. So we have two parameters. So the most simple case we can think of. What you have to realize is that your straight line that you fit is uncertain. There is a confidence region, a certain region where your line could be, and you have no, with real data that is scattered, there's no way to know for sure where it is. Moreover, if you do predictions, your predictions are uncertain. And you have to be aware of that. And now the thing is, what Fisher realized and laid out in his book is that this uncertainty actually depends on your experimental design, and that there is a rigorous mathematical way how to minimize them. The idea is to map the uncertainties in your measurements to the uncertainties in your model. So if you fit a model here, very easy, a straight line with two parameters, you have two parameters, as you can see in the top right, will be uncertain. So there will be a confidence region of your two parameters. That's a mathematical thing. That's something you can compute. And you can compute that in advance. Yeah, you can compute, okay, what is the expected uncertainty of my model? Now you have something you can optimize for. So you can maximize the information or minimize the confidence region, which is equivalent, depending on your experimental controls. And that's what DOE is all about. At the bottom right, there is a more modern picture of it that is depicting what is sometimes called iterative design of experiments or Bayesian optimization. So there we take the same idea and we take it a little bit further and we really formalize the prior information. So the information we have from preliminary experiments or expert knowledge, we take that into account and we plan the next experiment in an iterative fashion. What we also can do is we mix in Bayesian optimization the pure information with the objective we want to achieve. So we do not optimize for information only, but we optimize for the information about the optimum. That's a little bit more efficient. So with some more modern methods, we can be even a little bit more efficient than Fisher was 90 years ago. So now about Pareto optimization. So you have a model and you want to find the Pareto optimum in a high-dimensional space. So again, just for visualization, I take it in the two-dimensional space, and we have that curved line that you see on the top right. What is depicted on the top right is an easy sandwiching algorithm that approximates this Pareto optimization, Pareto optimum, the curve. The reason I'm showing this picture is that you are aware that we always have to work with some numerical approximations here. And that the underlying problem is very high dimensional and can be very nonlinear. So now the picture below shows how to visualize such a thing. This is important to understand how the software works in the end. So assume you have this Pareto front, yeah, for the objective A and objective B. And you are in the middle, like in this picture in the middle of the slide. And now you move on that Pareto front to the right. What is shown there are the projections on the A-axis and the B-axis. And if you move on the Pareto front in a certain direction, all the projections will move at the same time. All the projections will move, and they will move in opposite directions. So on the A-axis, you will move to the right. On the B-axis, you will move to the left. And that means that you are moving on the Pareto front from one optimum to the other. If some regions are not accessible or not acceptable, are forbidden, like on the bottom right, then you will see that certain areas on the projections will be forbidden. And to forbid one area in the objective space will result in multiple areas on all the dimensions, on all the projections being forbidden at the same time. And we will see that in the software nicely visualized. Here's already a screenshot of the software. What I want to emphasize here is that you can read about it. The paper on the slide before was more on the optimization methods. This paper here is about the application of the Pareto optimization in product development. And the specifics of that Pareto navigation, as we call it, is documented in patents. All right. So how do we actually design the solution? This is something I think is applicable to completely other situations as well. I mean, at the end, we want to provide something for our customers and we do a business on it. But everything is based on algorithms, based on very generic mathematical numerical methods. It doesn't make sense if everybody is developing these methods on their own. We would reinvent the wheel all the time. So we decided to open source the algorithms and actively look for collaborators. So for the experimental design methods and optimization algorithms that I've talked about, there's actually a GitHub project called BOFIRE, Bayesian Optimization for Iterative Real-World Experiments. Currently, BASF is already collaborating with Evonik and Boehringer, and we invite the entire world of data scientists to contribute. We take these algorithms, it's essentially a Python library at the end, and provide the functionality as a microservice in the intranet. So everybody in BASF can go to a URL, follow the logic of a REST API, and get optimization problems solved. That's the second step. That enables then solution development of all kinds of optimization solutions. Here in this case, there's a little bit of IP coming in from Fraunhofer Institute. That's the Institut für Techno- und Wirtschaftsmathematik in Kaiserslautern that we are collaborating with. And and this there, especially the navigation that I've talked about, is from them. And finally, we develop with our software engineers an application that is hosted on basf.com, so it's available to the customers and in-house. All right, let's talk about a specific case. We talk about exterior paints. Exterior paints, also called architectural paints, these are paints that you might use to, for example, paint parking garage. Yeah? So think about a big building, think about a big construction site, and you want to paint that. Our customer says, all right, in my paint formulation, there are already 15 ingredients in. This is a typical number for a chemical product. And don't touch it. This is my base formulation. I already know what it is. There might be some pigments for colors and whatever. That's what I have. But please make it better. And so we make it better by potentially 14 other ingredients that we have, that we can provide. And now the question is what to add and in what amount to the 15 already existing ingredients by the customer. These 14 ingredients are grouped into three different categories. So there are the dispersants, there are medium shear rheology modifiers and high shear rheology modifiers. There are technical reasons why there are differences between medium shear modifiers and high shear modifiers, but that's a detail. But there are three different types of ingredients. All right, so 14 variables from three categories. The objectives are as follows. So the customer already knows what the viscosity should be. There's a certain target. That's understandable. Think about a paint application. If it is too viscous, it drops. It's very dirty. If it's very dense and not viscous enough, it's very hard to apply. Yeah, and it's tedious. So there's a certain optimum. Now the challenge is to minimize the water uptake and to maximize the water vapor permeability. Now what is that? If you build a new building, the concrete is wet. There's still water in, and over time, it can take a year or maybe even longer. The water needs to get out of the concrete. So you need vapor permeability for the water to get out of the building, out of the concrete. But during that time, it might rain. And we are talking about architectural coatings. We are talking about buildings that are outside. So it might rain. So the water shouldn't get in. Yeah, the concrete doesn't it shouldn't get wet. And now you see the conflict. I mean, the water should get out, but not in. The mechanisms are a little bit different. So there are some physical um, effects, some ways how to manage that a little bit, but still there's a conflict. There's an inherent conflict. So you can't seal the building so that nothing gets in, because nothing would get out. So the software is a web application with a customer login and the BASF login. We try to make it simple. Again, the user is king, and the users typically tell us, hey, what you data scientists create is way too complicated. Yeah. So we try to make it simple. There are essentially two buttons, one for the workflow step before the experiments and one for the step behind, afterwards. So one for creating the experimental design, one for analyzing the experimental data for the optimization. So here I'm focusing on the latter because it's a little bit more instructive. So we assume that we have data. The picture is maybe a little bit small, but you can see that you have a lot of inputs, in that case here 14, and that you have a couple of outputs, in that case 4. What you might see is that if you look at the input data, that's not randomly chosen. That's not one factor at the time. This is well-designed data. So the people that we work with have already clicked on the first button in the first process step and designed the experiments. We have 31 experiments. Very typical number, small data. So we have to tell the computer what to optimize for, give them the target values for the viscosity, and tell them to minimize one property and maximize the other. Here's a very important point I haven't talked about so far. When you actually discuss the problems and you talk to the people, you find that there are a lot of constraints. Some of them are more obvious than others. The most obvious in a mixture problem is that the sum of all components is 1. If you do not take that into account in your design of experiments as well as in your Pareto optimizations, your predictions are off. You might predict formulations that are unphysical, that do not exist. So you have to take into account this constraint. The second constraint is of the kind that you don't want to have complex solutions. Even if they might have a little bit better properties, complexity is a thing. So people might ask you to say, okay, I have these 5 dispersants, but please take only 2 of them. But you have to take 1. So for example, a solution where all the 5 variables of the dispersions are 0 are useless. Yeah, we are not interested in them because we need a dispersant. But other solutions where all 5 of the variables are non-zero are useless as well because they are too complex, too difficult to handle. We call that the n choose k constraint. For example, choose 2 out of 5. And finally, there might be arbitrary constraints, technical constraints coming from the equipment. The duration of the experiment might be limited. There might be safety constraints. that are implicitly given. You need to be able to formulate them somehow as an equation to limit your optimization problem, to prevent you from predicting experiments that might be possible in a different universe, but not in yours. All right, and finally, you get a result. So I walk you through how the result looks like. On the top, you see the objectives. These are the variables I want to optimize for. At the bottom, you see all your inputs, all your factors. In this case here, the ingredients of the formulation. And the dots are the 1 point on the Pareto front. The dots on the bottom are the dots in the decision space, the ingredient, the solution. It's one solution. All right. First of all, you see you wanna restrict your problem. So your customer comes and says, I have specifications are always, something should be at a value plus minus something. I mean, in the real world, you never hit a specification exactly. Yeah, so there's a tolerance. So you put in what we call the delimiters, and you put in the specification by the customer here in terms of the viscosity targets. What you already can see here, and this again is very typical, there are a lot of red regions. Red means not allowed. Look at the input space. Most of the formulations do not fulfill the specification. Yeah? Most of your decision space, most of the experiments you could do are useless. In the next step, or I go one slide back. Now you have two variables left. Here, the capillary water uptake and the water vapor permeability. And now it gets interesting. Now you talk to your customer, because now you have an infinite number of solutions. You can slide on these, in these the dimensions, you can navigate on these dimensions back and forth, and you have your Pareto front. Now your customer will tell you what's more important. And in this case, the customer said, the vapor permeability is more important to me than the water uptake. In other words, it's more important that my building dries out fast. It's more important than how it gets wet. So we navigate to the right-hand side, and here on the fourth dimension, and we see the compromise instantly. This is what I mean with optimization on the shelf. Instantly, in a split second, we see how we have to compromise on capillary water uptake if the customer says, I want to optimize for permeability. Okay, and then they say, okay, there's 0.12, that's still fine. And on the bottom, you see your solution, you download it, and now we have one final step. This is a prediction based on a machine learning model, and on top of that, a Pareto optimization. So this is a numerical prediction. Do we know whether this formulation really exists? Maybe the model is wrong. Maybe we forgot about a constraint. So of course, we have to go back to the lab and test this formulation, this solution that we came up with the digital tool. Okay, it wouldn't be a success story if it wouldn't have worked. So here in this picture, you see the same variables a little bit differently are plotted. So X and Y are actually the viscosities. So the green area is actually the specification. So the green area is the region you need to be in to make to fulfill the customer specifications. The color code are the two variables to optimize for. So green is good, red is bad. And the dots are the experiments we did before. The dots are the experiments we started with. And you can see that, yes, we had a few experiments that fulfilled the specifications, but none of them were good. Some of them on the right-hand side, you can see were good in terms of vapor permeability, but they were really bad in water uptake. And the star, this is the solution we have selected using Kritos, and we have predicted using the model, and this is good. It's better in terms of permeability, so dark green versus light green, but that was the customer decision to prioritize permeability over uptake, but both is green, both is good, so the customer's happy, and we have business. All right. I want to conclude this talk by acknowledging that this is teamwork. It took us a couple of years and a couple of projects and a lot of work to get there. There is my team, the data analytics team, and there are some members listed here, but there are also the software engineers. Yeah? Machine learning is nothing without a good software that is easy to use. There are people in the digitalization unit or IT unit that make all these solutions possible. There are business development managers, people who think about how to actually create a digital business and how to link a digital business to existing chemical business. And there are the existing chemical business units, in that case here, the dispersion unit, with their colleagues on the technical side as well as on the marketing side who are involved. And last but not least, there are our collaborators at Fraunhofer Institute that we work with. And with that, I conclude my talk, and I'm very happy to discuss questions.
Thank you very much, Hergen. And indeed, and I think questions there might be throughout the chat. There were a few hellos, but now is your time to please question some of the things that you might have heard, challenge on some of those topics. So feel free to reach out. Once again, multi-platforms, so both on LinkedIn and YouTube. But otherwise, first of all, on behalf of everyone from Data Scientist, thank you so much, Hergen, for this very, very interesting talk and for showcasing some of the use cases. And I think some concrete examples of these applications are always welcome because the theory, very fun. Getting some practical examples definitely are too. So yes, maybe we just leave a few minutes for people to be able to reconcile all the info that they got across these past few minutes. And otherwise, looking for a few questions. I think this might be what happens when the talk is too clear. You get no questions afterwards. So that's just you know the how perfect it was. No, jokes aside, no, I think it was very, very interesting. On my end, I'm interested in saying what are the next steps. Oh, there you go. Sometimes there you go. Once I started speaking, a question popped up, so I'll put it up on the screen and read it out loud. Thank you for this nice presentation. What kind of machine learning methods do you use to make your predictions? From
Actually, there are two workhorses, I would say, in small data problems. One workhorse is the generalization of the picture in the middle. So start with what we call main effects. That means linear relationships. Add what we call interactions, which are collinear terms. And if there is an optimum somewhere, a sweet spot somewhere, then add quadratic terms. So really make the model step by step a little bit more complicated. This is one workhorse. The other workhorse is actually used for the plot on the bottom right. These are so-called Gaussian processes, which some people even call model-free machine learning, whatever that might be. So it's still a model. The model is to assume that let just this data speak and kind of spread out the information from one data point. Yeah, and how much this information spreads out is a hyperparameter, and this, in my words, essentially is a Gaussian process. The nice thing about the Gaussian process is first, it's nonlinear. So you don't assume anything about the structure of the model. You can model anything. And the second nice thing is it comes with error bars or with prediction errors out of the box. So these are the two typical models that we use.
And then we have another question from Julien, which I can put it up. How often would you recommend to have a chat with a customer to talk about specific constraints, specifically when you have no expertise of exterior paints? Now, I think this is generally speaking a wider question about exchanging with A, experts on one side, and then B, maybe business users or stakeholders when working on such a project.
Yeah. Also my experience, I'm now in the business since 20 years, is the more the better. It's hard to imagine a situation where you have spoken to your partner, to your user too often. The important thing is to include the partner from the beginning and to keep them involved over time. I think there is no one rule fits all how often you interact. It depends on how long the experiments take, how long your development takes, how close you are to the customer. So that might be more often or less often. The important thing is to start really from the beginning and to keep them involved until they made the final decision. Two things I want to add, especially from a data scientist perspective. I always tell my data scientists, go to the lab. Have a look how the data is captured. Yeah, because you will see that the table that you get only shows a certain window into the reality. There is other information that is actually available that is not in your data set and that might be important. Somebody decided that it's not important, but they haven't had your problem in mind when they decided that. So go to the lab, inform yourself how the data is captured and what a data is out there, what information is out there. So also this table evolves over the project time. And then there's a second recommendation from my side, what I also tell my data scientists, after you delivered your model or your optimization result, keep in contact, really ask them what they decided. Ask them a couple of weeks later whether the decision was right or not, whether it really helped. Try to get some feedback about your success, because a nice fit is not success. A nice optimum is not success. Even getting the bill paid by the customer is not success. Only if the customer really makes a decision based on your work and has success with that decision, is satisfied with the outcome, only then you as a data scientist can celebrate success.
Thank you so much. Then we have a question from Nicholas. So, is Pareto optimization used a lot in machine learning? As we've got no lessons on it during the data scientist training. I think this might be a student of ours. Um, Now, Hergen, of course, please feel free to share your opinion. I think here, Pareto optimization is more of a use case than a machine learning algorithm per se. But
Yes.
excited to hear
Yes.
what you
So
have.
what I've shown to you today is that Pareto optimization is kind of a next problem when you go into applying machine learning in practice. You see that your machine learning model is important, but it doesn't solve, it's not enough to solve actually the problem. You have to use the model in the context of an optimization problem to actually solve the problem. That's the message here. What I want to add is the methods that I've shown to you, especially this Bayesian optimization and again multi-dimensional Bayesian optimization, is also applied in hyperparameter tuning. So if you look into the details of your machine learning, yeah, into your own machinery, yeah, and you think about your own numerics as experiments, you have the same problem, and it's typically called hyperparameter optimization. I mean, you have typically many hyperparameters, and they are correlated. Yeah. So your hyperparameter optimization problem is a Pareto optimization problem as well. But this is deep stuff. I'm aware that in most cases we actually don't treat that as an optimization problem. But this is something I also advocate for, to think about the hyperparameter tuning as a mathematical optimization problem as well. And by the way, you can use Bullfire for that. Little advertising.
Thank you. We have a question from Julia, so I'll read it out loud. Is this valuable to adapt the experiment design method to have a more precisely mapped domain on the customer preference for parameters output, knowing links with the model? Now, that is a mouthful, but Hergen, what is your intake here?
Yes, I think also if I understand that correctly, or
And maybe
as I
Julian can let us
understand the
know, of
question, I
course.
would say answer yes, indeed. Uh, Design of experiments tend to go to the extremes. Yeah, the more informative experiments are actually not the experiments in the middle, the things you know that work. The most informative experiments are actually the extreme experiments that are somehow at the corner of your hypercube. And that, as a result, also maps the domain in the decision space. It gives you the extreme solutions, the extreme properties of your material in that case, that you can obtain. They are not necessarily optimal, so you still have to do the optimization, but they are, in a certain case, the extremes. Yes, and so mapping is a good word for that.
Thank you, and I love the picture, Julien, Garfield reference on the side. Then we have another question. What type of collaborations are you looking for? Are they more business-related collaborations? Or are they technical collaborations? Indeed, there was a call to action to find partners, so maybe you
Yeah.
can enlighten us here.
Yeah. So two very specific answers. First is, if you're interested in Bayesian optimization, if you are great in numerics and coding, especially Python, look at the Bowfire project on GitHub. Think about collaborating. Think about joining. Yeah. Yeah. Here, GitHub.
There
There
it
was
is.
link, github.com/experimentaldesign/Bowfire. This is a real open source. This is not fake open source. Uh, think about joining us. For example, a former intern of ours who left the company meanwhile is still on board. He's still part of the team. Um, and the other is at the top, at the bottom of that slide. If you are in the business of, yeah, buying chemicals for formulation, so if you are by accident or whatever a customer of BASF, think about it. Go to kritos.basf.com. Think about whether you can actually use that tool to optimize your products with the help of our digital tool, and just send us a message and we are in business.
Thank you very much. We do have a few thanks along the way, but thank you very much, Hergen. I think we're down to the last questions, but we can still, or at least we want to talk on your behalf, Hergen, but still have a few minutes in case there's any more that pop up. So don't hesitate to put any more questions that you may have. All right, I think we might still wait for a couple more minutes, but in any case, I can take the time to thank you very much, Hergen, for presenting and being here today, for the very valuable insights that were showcased, the very nice kind of vision into what you've built and you know, future steps for your projects, with some great collaborative ideas as well. So thank you very much for your time. It's really been a pleasure. Thank you to everyone also attending today, for tuning in and listening into our very nice webinar series. We'll be back with more webinars with a variety of more business or more research related topics in the weeks to come. So stay tuned and don't forget to maybe subscribe to our different social media pages to stay updated and stay in the loop. But otherwise, I don't think if we see any more questions in the next couple seconds, I think we can call it a day. Thank you so much, Hergen, for accepting our invite. It's really been a pleasure, and we look forward to seeing how Krytos develops in the months to come.
Very good. Thank you.
Thank you, everyone. Have a great day. Goodbye, and see you very soon on a data scientist webinar. Goodbye.